Hey guys, this is Terence. Welcome to the new episode of RhinoPython and JH Playground. Before starting today's video, I want to say thank you to all of you who are watching or watched my video, who subscribe my channel, and who leave likes and comments under my videos. Thank you so much. And your support encourages me to keep working on the RhinoPython and JH contents week by week. So now I'm feeling more confident in doing these tutorial-like videos. I don't want to define my video as tutorials because I'm just kind of sharing my knowledge about Rhino, about Grasshopper, and about Python with you guys. So anyway, thank you so much. And today's topic is how to use the Bezier curve to create this set of patterns, to create these shells. But the RhinoPython API, the RhinoScript syntax, which we are very familiar with, this API doesn't have any Bezier functions. So we need to jump into another giant and even more powerful library, which is RhinoCommon, to experience the real power the Rhino cells can provide us with. And let's go. I think all of you can access Wikipedia and check more scientific explanations of the Bezier curve on this page. So I choose not to read these terms. Instead, I prefer to explain this geometry more practically or straightforwardly. So let's open up the Adobe Illustrator and use the pen to draw an arch. The first point and the second point here. And this is the Bezier curve. It is a neat looking and structurally reasonable geometry controlled by two anchor points. These are two anchor points and two handles. These are two handles. If you want to modify this shape, you just need to modify the position of these two handles. Then you can get the unlimited possibility just using these 4 points. Now, assuming that we have the wall under this arch, and now connect the arch with the wall. I want to shift this a little bit for a further explanation. Move this point here. If you want to get a smooth transition from the wall to the arch above, you just need to make sure that the handle's X position is same as the hinge's X position. Then you get a smooth transition from here to here. I mean smooth transition is that there's no acute or noticeable angle between these two components. If the shape looks like this, there will be a noticeable transition or noticeable angle here. So to make the transition smooth, we just need to ensure these two positions. Okay, and for sure you can modify the Y position here to make some part of arc higher, but some part of the arch lower, like this. And this is the fundamental of today's pattern. Now let's create this prototype with Rhino and Grasshopper with some codings. Let's first set up our work environment. So at first I want to create a node, create a rectangle with the height and width of 10 here. Then I can add the GHPython node like this, remove these two inputs, right click, choose show code input parameter, and also confirm input is path. Add the file path node, file path here, right click, synchronize it, then select one existing file, which is this file, our GHPython file here. I want to first add a panel here to check if these two files are successfully connected. So here I prefer to say print go. Save it. Now you can see the word go shows up here. That means the Python file is successfully connected to our node. Now we can remove this code and add an input here called poly, which is a polyline from this node. Right-click this input, set the type to the curve. The polyline is actually a line-like curve, so I prefer to set it as curve just for safe. And inside the code here, we first import the RhinoScript syntax as rs. Then we need to import another library as I mentioned at the beginning of this video, which is the Rhino Common. We can say rhino.geometry as rhg. This library has the Bezier curve class we needed to build our shape today. So below here, let's define a function called add Bezier shell with an input polyline. And first we need to declare an empty list called Beziers equals to an empty list. Okay, and we need to extract all the points on this polyline. We can say points equals to rs.curveEditPoints. We put the polyline inside here, then the points represent all the points on this polyline or on this curve. Below that, I can say PTA is the first point equals to point at index 0, and PTB equals to points at index of 1. Let's return these 2 points to check did we extract the correct points. PTB, okay. And down here, let's call this function called a equals to equals to add Bezier shell and with a polyline. Now you can see here on the Rhino workspace, you can see we extract 2 hinge points. Based on these 2 points, we can just build a single Bezier curve as the instance. Think about what we need to build the Bezier curve. We need 2 hinge points and 2 handles over them. But please notice that as we want to use the Rhino Common library, we can't directly use this point to create the Bezier curve. We need to convert this point into the Rhino Common point 3D classes. So please follow me doing this. I need to modify these 2 lines of code as rhg, which is our new library, dot point 3D is a 3D point class inside the Rhino geometry Rhino Common library. Then here we just put points at index 0. We do the same thing here, dot point 3D pts 1. Now we successfully convert these 2 points into the Rhino Common class points. And you can see the 2 points are still here. That means our conversion are successful. The next step is to define how high the handle is. My solution is to use the span of these 2 points as the height of the handle points. Let me do this. First, I should calculate the span between the point A and point B. Say rs.distance PTA and PTB. Sorry. Then we first create the A handle. For sure, it should be a Rhino Common point 3D class, point 3D. But this time we don't put the point inside here. Instead, we will put the x, y, and z coordinates into this parenthesis. So the first one should be point A's x coordinates. The second one is point A's y coordinates, and the third one here is point A's z coordinates plus the span. And the same rule applies to the B handle here. Modify this to PTB, 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 and save it. Now we also return these two extra points, A handle and B handle. You can see all the 4 points are showing up on our workspace. Point A, anchor, or anchor A, anchor B, handle A, handle B. Now we have this point, we need to use this point to create a Bezier curve. We will need a function called equals to RHG dot Bezier curve with all the points. Let's put all the points into these parentheses as a list. Say PTA, PTB, should be PTA, then A handle, B handle, and PTB. It should be this sequence, but now you can see there is an error here. Multiple targets could not match. This is because, as we just mentioned, this function is a Rhino common library function. So this function cannot accept the Python list. Instead, this requires the point3D list. It sounds pretty weird, but let me just bring up the API. Then I think you guys will be more clear. And here, let's first check the Bezier function here. And we have this Bezier curve constructor. We can click this. In this part, you can see it requires a point3D list as an input. But what is the point3D list inside the Rhino Common? It's actually this one. Let me type the point3D list. And we can see, where is it? This one, point3D constructor. This constructor will convert all the points into a point3D list. But this one belongs to another library. It's no longer inside the Rhino geometry, but it's inside the Rhino.collection library, which means we need also import this library called Rhino.collections as RHC. And now let's put all the points into this point3 list. Let's do point pt list equals to RHC dot point3D list. Then we put these 4 points into the parentheses and replace this part with the pt list. Save it. Let's see. No errors here. That means our code is successfully executed. But it's quite weird that, oh sorry, I forgot to return this Bezier curve here. Yes, as you can see, even though we return this Bezier curve, we still can't see the curve inside our workspace. That's because the Bezier curve geometry is not visible in Rhino's workspace. It is just a data type with a lot of internal computations. So we should convert this Bezier curve into the NURBS curve to make it show up in our Rhino workspace. What we need to do is just Bezier dot to NURBS curve with a parenthesis, because this is just a method. Save it. Oh, it still doesn't show up. Oh, sorry, I forget an important step, which is replace it with the original Bezier curve. Save it. I think it is here. Yes, we successfully generated our first Bezier curve. Our next step is to add some controls over the shape and make it go slightly beyond the regularity. So we can add a z factor here to control the arch's overall height. I can say this, add an input called z factor here, and set the factor ranges from 0.5 to 1.5. Then connect this slider here, and we can multiply our span with the z factor to allow this slider control the height of the arc. We just do this, z factor, save it, and you can see now we can control the overall height of the Bezier curve. Then we can also add some randomness on each handle's z coordinates. But before doing so, I want to first import, I should say from random, import two functions. First one is random, and the second one is seed. Sorry, seed here. I want to use the seed to have control on the randomness of the how to say, to control the randomness of the shape. So I first need to call the seed function here with the input rseed, and on the GHPython node here also add an input of rseed, then input it with a very large integer value here, save it. Then we can add some randomness over each handle's z coordinate here. I can say I can add this with random multiplied by 2 minus 1. This part generates a value, a random value ranges from -1 to 1, and it is a decimal or float value. Then multiply by span. Also add this part of code to here, save it. And I want to make the arch slightly lower and use this part to control its randomness. Now you can see our Bezier curve becomes more dynamic than the ordinary one we just created several minutes ago. Then we will apply the same rule to another side of the square of the rectangle. We don't actually need to modify the major body of this code. Instead, we just need to put the Bezier generation function into a loop. Now let's do this. Above here, we can say for I in range start value 0 and value length PTS -1 with a step of 2, comma, oh no, it's colon, okay, indent it, make all this part into this loop, and here we just need to change this to I and I plus 1, and at the end of this part, we need to append the Bezier into the list Beziers. Now we can say Beziers dot append Bezier. Then what we need to return is Bezier now. Save it. Now we can see we have two Bezier curves here, and slightly adjust its height and randomness. Okay, and well, and add a node called loft here. Apparently, this shape is definitely not what we want. The reason of this twisted loft is that the direction of the two curves is inversed. This curve's direction is like this, but this one is reversed. So they are inversed. To address this problem, we just need to add one line of code at here, just below, once below the Bezier curve generated, we can say if I equals to 2, Bezier dot reverse. It's a Bezier curve class method. Save it, and things goes back to normal. And I think this is the unit we want. We can use this unit to create the repeated pattern. It's time to get rid of this single module. Now we can create a new node called rectangle. Yes, it is. And size X. What we are doing now is create a grid that we can duplicate this pattern to each of the rectangles. And the X size is 10. Y size, maybe make it 9. The number along the x-axis could just 6, and this could be our basic grid, and we will do the Bezier shells on each of these cells. Then we just remove this input, remove it, and remove this part of code. Change the name from poly to polys, make it semantically correct. Move the node here, connect it to our RhinoPython nodes. Then we should use list access. Not reverse. We should flatten this data structure, make it linear structure here, and remove these nodes in case of any unexpected errors. And inside the code here, what we need to do is first declare an empty shell list called shells, and loop over each of the polylines inside this generated from this node. We can say for poly in polys. Then the shells add equals to this function. Poly, yes, I think so. And let's change this name to shells. I hope this works. Save it. Okay, we have what we want. The next step is to loft each pair of Bezier curve. We need to first use the dispatch node. Is to divide these curves intermittently. Then graft each output, check the data type. I prefer to simplify it. Simplify and graft. Make the data structure looks neat. Loft the first one, the second one. Okay. Yes, we have our shells. Now, as you guys can see, these shapes are now still not satisfying because all the shells are now facing the same direction. We want some shells like this one facing another direction, and this one facing another direction. I just want to make it randomly. So very simple, just inside the add Bezier shell function, and add a start point, start P pt equals to rand int 0 and 1, yes, and change this value to start point. The new code means the start point could be either 0 or 1. If the start point is 0, this code will create two Bezier curves like this. But if the start point is 1, the function will generate the curve in the not opposite, in another direction. Okay, so I think we still need to modify this part called start point plus 2 to ensure the opposite curve could be reversed, then the loft result will be correct. Save it. And guys, look at this. We basically created what we want today. Congratulations! We finished our production process today, and I know some of you guys might ask why our product's layout is slightly different from that of our cover of this video. That's because I used a mathematical knowledge called Euclidean algorithm. Let me bring this up. This is the Euclidean algorithm. Well, it's kind of crazy. I use this algorithm along with the programming knowledge called recursion to subdivide my plan. And these 2 points are going to be the next week's topic. So that's it for today's video. I'm super welcoming all of your comments, suggestions, and critics, and you can let me know your thoughts about my video contents and my ways of narrating in any ways you want. So that's it. Bye bye.